Hi there, my name is Dr. Alan McCue and I am the course coordinator for the Oil and Gas Chemistry Masters Programme. So I'm here today to give you a taster lecture to see what it would be like to study at the University of Aberdeen. And this comes from my course on flow assurance. So what is flow assurance? Flow assurance is all about making sure you can get oil to flow from a reservoir to a processing or refinery facility and the challenges with making that happen. Okay, so let's start off by thinking about the reservoir. So a reservoir is a collection of permeable rock surrounded by bedrock. Now, the environment will be high pressure and moderate temperature. So what do I mean by moderate temperature? Typically 60 to 80 degrees Celsius. Within the permeable section, there are a collection of fluids. So two of these are hydrocarbon based. So we've got what we would class as oil, and then we've also got gas. Now, it makes it sound a little bit simple, but you've also got what we'd call condensable gases. So because the reservoir is at high pressure, a portion of the hydrocarbons that would normally be gaseous, so they would be in the gas phase if they were at atmospheric temperature and pressure, would have condensed, so they'll be present in the liquid form. So that's the two different sources of hydrocarbons. As well as that, you've also got water, so that can be formation water, so that's water that's naturally present in a reservoir, or it can be injection water, so that's water that we push or force into a reservoir in order to help with oil recovery. So we've got all these different fluids, and that's what they're like in the reservoir. But what happens when you move out with the reservoir? Well, first thing that happens when we open up a reservoir and start to remove the fluids is that the pressure within that reservoir will decrease. Now, as pressure decreases, the condensable hydrocarbons will be likely to regasify, so go from the liquid phase to the gas phase. Now, that's within the reservoir. Outside the reservoir, so once we get to our wellhead here, there's going to be significant changes. So the pressure of our fluid is going to decrease and decrease significantly, and the temperature is also going to decrease. So I said the reservoir was around 60 to 80 degrees Celsius. If we think about an example of an offshore well, and that's really appropriate because Aberdeen is synonymous with the North Sea oil industry. So we think about an oil field in the North Sea. The temperature of the seabed is around 5 degrees Celsius, so it's considerably lower than you would anticipate in a reservoir. So our fluids are going to change. Now, the fluids have got quite a long journey, potentially, to go from the oil field to the processing facility. So if you're lucky, that might be 20 or 30 kilometres. In most cases, you're speaking about longer distances, so perhaps upwards of 100 kilometres. And over the course of that time, our oil is going to continually cool down, and it'll eventually cool down until it reaches the ambient temperature, so the temperature of the sea around the pipeline. So what impact does that have on our fluids? Well, before we think about that, let's just have a look at a map of the North Sea here. So each of these dots represents a different oil field. It would be fair to say that within a particular basin, for example the North Sea, you'd anticipate that all reservoirs would have a similar type of oil, but they will all be subtly different. So that's really important, because if we look at this network of pipes, so the green lines represent the oil pipelines, the red lines represent the gas pipelines. What you'll see is that there are all these fluids come in through almost exclusively through one pipeline. So this is the Forties pipeline and comes onshore just north of Aberdeen. All these different oil fields feed our hydrocarbons, our fluids, our water as well, into one pipeline. So they start to mix, and all of these oil fields will produce oil with slightly different composition. So the question then is, what happens when these fluids mix together? And this is the whole crux of the challenge of flow assurance. As well as that, each of these different oil fields will be operated by different companies. And different companies will have different ways or different preferences of how they extract hydrocarbons from a reservoir. As well as that, they may use different chemicals to enhance recovery. So all of these different factors means that once you get to this pipeline and all of these fluids are forced together, how do they mix? How do they interact? Does it create any kind of problems? So this is a multi-phase problem. And the key thing is we've got different phases, or different fluids rather. So we've got water, we've got oil, and we've got gas. And we've got to think about what happens to these fluids as temperature and pressure changes. So as I said, the pressure within a reservoir is going to drop. The pressure within a pipeline is going to drop. And the temperature within a pipeline is going to drop. So these are the challenges we have to deal with. So let me come back to where I started then, which is, what is flow assurance? Flow assurance is a term which describes the all-inclusive term for low-risk and cost-effective delivery of multi-phase mixtures in the oil and gas industry. So what does that really mean? Well, it means I need to make sure I get oil and hydrocarbons from my reservoir to my processing facilities without interruption and without it costing me lots of money, because as soon as flow stops, I am losing money. I'm losing significant amounts of money. So, if we look at this statement here, there are 5 primary types of solid which can form whilst these fluids are flowing through a pipeline, and they all present different flow assurance challenges. Now today, because it's a taster lecture, I'm only going to talk about one, and that is waxes. So, what is a wax? Well, waxes or paraffins are a general name for a group of hydrocarbons, so with varying chain length, so roughly between 6 and 60 carbons long. That would be the chain length, and you speak about mostly linear waxes. They can have low or high molecular weight, and the problem with these waxes, particularly as they get to longer and longer chains, is that they are sparingly soluble. And in fact, they're only soluble to any significant extent at elevated temperature. So once you get to 60 to 80 degrees, as soon as that oil starts to cool down, the solubility decreases and the hydrocarbons or these waxes are going to crash out or precipitate, and that's going to create some problems. So what happens when they precipitate is they form these needle-like crystals. So if you look at this beautiful cross-polarized optical microscope image, you see that we get these needle-like structures. So these are essentially solid particles within our fluid. Now, what's really happening here? So there are 3 key steps. So we refer to these as nucleation, precipitation, and deposition. So if I look at the sketch down here, imagine each of these yellow circles represents a wax molecule. If I want to form a nucleus, I need to get 2 or more of these wax molecules to come together, so they stick together. And after they do that, they can aggregate and grow. If they grow beyond a certain level or certain size, then they will precipitate out. So what does that mean? They're no longer soluble in the fluid. In other words, it's like having a solid particle in my fluid. Once they precipitate out, they can crystallize, they can continue to grow, and they may deposit. Now, where are they likely to deposit? Probably on pipe walls. Now, that's potentially a problem, because if they deposit on the pipe wall, as we'll see in the subsequent slides, that creates some flow assurance problems for me. So keep in mind these 3 steps: nucleation, precipitation, and deposition. So let's think about this wax in a little more detail. So let's think about some wax characteristics. Now, to do this, let's imagine we've got a sample of crude oil, and I'm going to heat it up to reservoir temperature, so around 80 degrees Celsius. And I'm going to let that cool down. So what happens? If I heat it up to 80 degrees Celsius, all of the wax dissolves, so there's no solid particles. As I let that cool down, the first thing that happens is we get some nucleation happening, and then we start to see some precipitation. So this happens at what we call the wax appearance temperature. So that's the temperature when wax begins to precipitate. Now, for most crude oils, this typically happens in the temperature range 25 to 40 degrees Celsius. So if my pipeline sits in an environment where the temperature is similar or lower than this, then I'm going to have wax precipitating, and that's going to create flow assurance problems. If I'm producing my oil in a country which has got a much warmer ambient temperature, so if you think of the Middle East, where you've got onshore reservoirs and the temperature is going to be hotter, I might be lucky and I might operate above the wax appearance temperature. In that case, waxes won't be a big flow assurance problem for me. If I let my oil sample cool down below the wax appearance temperature, what happens is these wax precipitates start to cluster together and they organise like a 3D network in the fluid. Eventually you reach the gelation temperature. So the gelation temperature is the point where my fluid now behaves more like a solid than a liquid. So this 3D network is big. It covers all dimensions of the fluid. If I decrease the temperature below that, I eventually reach something known as the pour point. So this is the temperature at which oil stops flowing. So if you look at this picture here, this is quite a good example. So this is an oil here in this beaker which no longer flows. It's essentially solidified. Now if that happens in a pipeline, that's bad news, because I cannot get oil from my reservoir to my processing facility. So in other words, I don't make any money. Now, what sort of temperatures do oils solidify at? So what temperature does the pour point occur at? It depends on the composition of the oil, but typically below 0 degrees Celsius, maybe well below 0 degrees Celsius. So I'm unlikely in the North Sea, for example, to operate near the pour point. However, if you think about the temperature of a seabed, around 5 degrees Celsius, I'm going to be operating below the wax appearance temperature, so wax will precipitate and potentially deposit. So what issues do these waxes cause? Well, there's two issues and they end up with the same negative consequence. So the first one is wax precipitation increases fluid viscosity. So if you imagine putting something solid into a liquid, it gradually becomes more viscous and does not flow very well. A nice simple example of this is if I imagine having a pan of water and I dissolve some sugar into it. If I keep adding sugar, eventually that becomes thicker and thicker and thicker, and it doesn't pour or flow very well. The same thing happens with oil if wax precipitates. As well as that, wax can deposit on the walls of pipelines, and this decreases the internal diameter. And we've got some excellent pictures of this. So these are pictures of different oil pipelines where wax has deposited, and you see how big a decrease of the internal diameter you have. So wax deposition is a big issue. Both of these factors manifest themselves in the same way, and I get decreased flow rates. So I can't get hydrocarbon from reservoir to processing facility as easily or as quickly. You get the odd example where the precipitation and deposition is so bad you essentially block up the pipeline entirely. In this case, you might have to pig, that's the technical term for mechanical scraping of your pipeline. So you push all of that blockage out, and you end up with this fantastic looking image here. So this is essentially a solidified lump of wax. So what can we do about waxes? So when things go wrong, we have to remediate them. So if I've blocked up my pipeline, I've got various options. Now, the first of these is a thermal treatment. So we know wax deposits and precipitates because temperature decreases. So I could do the opposite. I could increase temperature. I can do that by adding in a hot fluid. That would be a good way of doing the opposite. Or I can find some way to heat my pipeline. That could either be via external heating. Now, if my pipeline is short, that might be viable, but if my pipeline is 100 kilometers long, that's going to be expensive. The other alternative is I could make a chemical reaction take place in close proximity to where my wax has deposited. So if I have, say, a simple reaction between an acid and a base, that will generate or release heat because it's exothermic as a reaction. If that happens, that heat that's generated might be sufficient to redissolve some of the wax. I've I've also got some options to use chemical treatments, so I could try and dissolve some of the wax that has precipitated and deposited, so perhaps adding in some kind of solvent, perhaps a xylene-based solvent, or I could add something which will break up the waxes, so a dispersant or a surfactant. Lastly, and when everything else has failed, you've got the option to have some kind of physical remediation treatment. So if you remember the image about pigging on the previous slide, mechanical scraping of the pipeline. Okay, so wax precipitation and deposition is a thermodynamically controlled process. It happens because the solubility of a wax decreases as temperature decreases. In other words, this is predictable. We know it's going to happen, and if we know it's going to happen, we can try and control it. So we think back to the 3 different stages. We've got nucleation, precipitation, and deposition. I can try and find a way to target each of these, and that might help me stop wax deposition and precipitation take place. So let's think about stopping nucleation. So if I'm going to have nucleation, I need to have 2 or more wax molecules coming together. They need to stick together. So what I need to do is find a way to space these all out. Keep the wax molecules far apart. I can do this with something known as a wax dispersant. So what is a wax dispersant? This blue box gives you an example. This is dioxyl difficult word to say, dioxyl sulfosuccinate. Here we go, I've got there. And this is an interesting structure. So on the left-hand side and on the right-hand side, I've got an aliphatic hydrocarbon chain. So that is very similar to the structure of a wax. So wax is just a long straight chain alkane. Now a good rule of thumb is that like interacts with like. So if 2 molecules are structurally similar, they will want to interact. So my wax molecules will like to interact with either end of this wax dispersant. Okay, so that's good. What about this bit in the middle? This bit in the middle has got lots of electron density. It's polar, okay? Waxes are non-polar, so this part repels waxes. It's the opposite of a wax, if you like. So if I can get this molecule to interact with a wax molecule, and it can do that with either end chain, this bit in the middle will help to repel or push away other wax molecules. In other words, I can stop nucleation. The other option is, let's not try and stop nucleation, let's try and stop precipitation. So let's accept the fact that these wax molecules will cluster together, and let's try and stop them from growing. So I can do this with a wax inhibitor. So this is typically a big polymer that can wrap itself around or hug the wax crystal as it grows. And when it hugs that crystal, it stops other wax molecules from binding onto it. The other thing I can try and do is stop deposition. Now in this case, I'm basically accepting that nucleation and precipitation will take place to some extent, but as long as the wax stays with the fluid, as long as it doesn't deposit on the pipe walls, then my fluid viscosity increases, but my pipeline diameter does not decrease. So I'm making the best of a bad situation, if you like. Again, we can stop deposition to some extent with either surfactants or dispersants. So here's another alkyl sulfonate. And what you have here, again, is you've got an aliphatic or wax-like part of the molecule that likes to interact with it. And then you've got something which is polar, so something which repels wax molecules. Now, in all fairness, there's very little difference between the molecule in the purple box and the molecule in the blue box, and that's because a lot of wax dispersants affect both nucleation and deposition. Lastly, what can I do? Well, we know wax deposition and precipitation is caused by the temperature of my fluid decreasing, so potentially I could stop the temperature decreasing by insulating my pipeline. Now, there's a lot of detail on this slide if you really want to look at it, but basically, if I stop heat exchange between my pipe and the surroundings from taking place, so insulating the pipeline, then the rate at which my oil or fluid cools down decreases, and wax precipitation, the rate at which that happens, decreases. Now this doesn't stop the problem from occurring, but it slows the rate at which it happens down. And that can be beneficial in terms of flow assurance. So that is the end of my my sample lecture. I hope you found that interesting. If anybody has any questions, feel free to contact me. The slide, my contact details are on the first slide. I hope you find this topic interesting, and this is just a little snapshot of what it would be like to study the oil and gas Master's Chemistry degree at the University of Aberdeen. Thank you.